Today, in this particular tutorial, we are going to learn how to run a band structure calculation. Of course, definitely at first the prerequisites. You should know how to run a self-consistent field calculation. What we have already discussed in our previous lecture. Along with, you should have converged K-points, converged energy cutoff, and a structure after doing the relaxation calculation, right? So, we are going to start exactly from the point where we have left in the previous tutorial. We did perform the relaxation calculation and we had a structure. So, that is the relaxed structure, right? We are opening it using Burai. Here it is. Okay. So, let me just go to geometry, maybe SCF, whatever. Of course, you are not going to run band structure calculation from here. You can also go to bands, but that is not going to serve any purpose. Okay. Well, this is the lattice parameter after relaxation. So we have to modify the SCF according to this. So let me just open the previous SCF file, SCF input file, of course. Okay. Let me just paste it here. Okay. And we are going to need a new parameter here, that is NBND. This is called N band. Okay. Technically, this is the number of bands you want to calculate. But what is the number of bands we want to calculate? That's the question, right? You see, what is the material that we are calculating? That is BaTiO3. Now, barium does have 56 electrons. Titanium does have 22 electrons. And for 3 oxygens, we have 8 into 3, that is 24 electrons. Okay? So, in totality, there are total 102 electrons. The number that we are going to put here is actually half of that. So is it exactly 51? Nothing else? No. It should not be less than 51. You can definitely increase it. There is no problem. But since it's an insulator, 51 is the lowest bound. Okay? If it were a metal, then you would have to take 20% above that. Okay? So if it were a metal, maybe we would have taken 61 or 62 instead of 51. Okay? Well, so my suggestion is always take 20% extra. Okay? There is no harm in that. For this calculation, we are actually going to make it at 70. That is not going to miss any band. Okay? This is for, better security. Okay? Now we are going to need another new section here. That new section is called and bands. So let's write that. Okay. And every section ends with a slash, right? Don't worry, we are not going to write many things here. Just one single line. Okay. That is L sim. That is L symmetry. Don't worry, I will tell you what is that. Equals to what we are going to use in this calculation is false. And every time you should use false here. Why? You see, in the classes of basics of DFT, especially in this particular lecture, we had learned something called irreducible representation, right? So that is a symmetry reduced representation. If you write L symmetry equals to true, then only the bands for this irreducible representation will be calculated, not for the whole structure by itself. Okay? So to get the whole bands, you should write false. And that is recommended every time. Okay? Another thing that we are going to change here is this. It's not going to be automatic anymore. Okay? We are going to write TP bar D. So that is a particular format, but how does it occur? Okay, so that is the paper we are going to talk about, and let me directly go to electronic properties. And if we go down, you will see the band structure of BaTiO3. Now take a look at these points. These are the K points, right? So how many K points they have taken? 1, 2, 3, 4, 5, 6, 7, right? So if we are going to do the calculation according to that, if we are also going to take 7 K-points for BATIO3, then that number is what we are going to put here. It could be 8 also, it could be 10 also, it could be 5 also, whatever you want. Okay. But how to choose the K points and how to choose how many number of K points you are going to take? That is the question, right? There are two options. One, if there is an existing literature of that, obviously you can take the K points from that. Especially if you are a new researcher, and then generally what happens with a new researcher is that if you wants to ask how much validity does your research have, is your research even correct? Then you can take these things as differences and say, you see, this particular band structure is the same as have been calculated previously in that paper. So that is one point. Another thing, if you do have a whole new material, or if you are not taking the same band structure that have been calculated before, but you are trying to find some new thing, then what you should do, right? So let me open Google Chrome here. A very useful website for this particular purpose of choosing K points is CKpath. Okay, just search it in Google and see that's the website we are trying to find. Let's go there. Okay, now we are going to upload the CIF file, the one we have got after the relaxation calculation. So just choose that. So I'm going to go to desktop and PC Relax. This CIF file I'm going to choose. Okay. Of course, this is a CIF file, so just choose CIF and click on Calculate My Structure. Okay. And you see, you can interact at this particular reciprocal lattice also, but that's not the point here. Let me go down. You see, they have given you a suggested path. That also is something you can take. Of course, you can take this whole, or you can take only up to x. What does this mean? This sign actually means that this x and r are not directly connected by a straight line. So there is no path from x to r, okay? That r is a disconnected point. So for simplicity, we can also take gamma x m gamma r x, okay? So let's do that. How many points are there? 1, 2, 3, 4, 5, 6, right? So in that particular input file, let me write 6. And what were the points? Gamma. For gamma, we are going to write GG. Okay. So this gamma is GG and XM gamma RX. That is what we are going to write. Okay. Yeah. Let me write X, M, gamma, R, X. Okay. And just take a look at this particular band structure. So they have gone from gamma to X, right? And these points have been calculated. But you see, really this is a numerical calculation. So this is not continuous. The point is, how many points should we take from gamma to X? Obviously, the more number you take, better is the interpolation and better is the graph quality, definitely. So what is the rule of thumb here? The rule of thumb is take 40. This means while going from gamma point to X point, 40 points will be calculated in between. Okay. So for X also, we are going to write 40. Similarly for M, 40, and goes on like that. Now, what should we write for that last point? Because we are not going anywhere from here, right? So, even if you write 40, only one point will be calculated, that is x, because there is no point after x. Okay, if there were a point, let's say w after x, then from x to w, it would have calculated 40 total points. Okay, we can also write 1 here and we can also write 40 here. Whatever you write, only one value will be taken. Okay. Okay. Everything else will remain same in this particular calculation because atomic positions have not changed after the relaxation calculation since it was a cubic. If atomic positions have changed, then you go to this particular input file from Burai and just copy these atomic positions. You see that is in angstrom. Obviously, as I have told you, you should always do this crystal and just refresh it, and you should copy this and put this in your new SCF. Okay, but after the relaxation for BATIO3, atomic positions have not changed. So we are going to keep that, and let me just save it. Okay, so the SCF file is now complete. Okay, now we are going to be clever. Okay, we will just write bands here, and we are going to save it as a new file. Let's say BATIO3 band starting. And obviously, we are going to do all files here, save. So let me take a new text document again. Now we are going to write the commands to run this band structure calculation. And this is tricky, okay? Be concentrated here. The comments are, at first, definitely we have to run a SCF calculation. So just do PW less than, just go to this particular folder in desktop, and let me copy this name and just paste it here. That is the input file name. I have told this many times in the previous tutorials. And let me just paste it here, dot out. Okay. Then we are going to run another PW calculation, but now with bands input. Okay. So we have renamed it as bands dot in. Maybe we can just copy this for the output file name dot out. Okay. And now we are going to run the bands calculation. Okay. So do bands less than that same BATIO3 bands dot in, close the bracket, and we are going to write anything you want. But one thing that you should not write is bands dot out. This is absolutely not recommended, because Quantum Espresso itself is going to create a bands.out file. Okay, then your file is going to confuse the software only. Okay, and you may get wrong results. Okay, so don't put this in the output file name. Do anything else you want. Okay, maybe you can do bt bands.out. Okay, so let me save this also, just to do save as. Okay, maybe bt bands dot back. Okay, we are going to write all files here and save it. Just close it now. Let me close Burai also. We are not going to need this anymore. Okay, now this is the VC Relux folder, right? So let me just take this batch file, the input files, and the pseudopotential files. Obviously, the pseudopotential files, the details of these, how to get these, all that I have already described in the second tutorial of this lecture series. If you are getting confused here, you can go to that second tutorial. And also, I have put all these files in the description box of this particular tutorial. Let's copy this. And let me put this in the folder where I have kept the Quantum Espresso. I have kept it in C drive. Maybe you have kept it in another directory. Does not matter. Just paste it. Okay. Now right click at any place and open in terminal. Dot slash, the name was bt bands.bat. Just do there. So now it is running. Okay. So it will run for some time, and then we are going to come back once it finishes. While this is running, let me tell you the essence of the band structure. What exactly we are doing here. Okay. You see, Electrons does have specific orbits, but that's for a single atom. When two atoms comes closer, then what happens? If two electrons are having same energy, when they come closer, they will divide into different energy states separated by a very small amount of energy. Now, that is for two electrons only. When too many electrons are coming together, then non-trivial interactions happen, and what we get is a several splitting of this one particular energy state. Okay, and what we get is the energy band. So that band is what we are calculating. How will the energy states look after the crystal has formed? Okay, well, so let's wait. Let me first forward the video here. Okay, so the runs are now complete. Let me just minimize this, and you see all the output files are here. I will just copy all these output files. This PWA shape, this is actually the wave function file. Okay, this is not what we are going to need. Quantum Espresso calculated these wave functions for its own purpose. Okay, so that it can calculate the properties that we need. Okay, okay. So let me just paste it here. Okay, these are the output files. And now we are going to plot this. We are going to plot this in origin. So let me just open that. Okay, close it and close that too. We are going to take a single ASCII, right? And this GNU file, that's what we are going to plot. Okay, just okay, just plot it. Okay, okay. So that's the plot, and you see, this is a energy band. Okay, but what we are going to need is the intricate details. Okay, we are just minimize this now. Go to scf.out. You should search for Fermi. So now you see Fermi energy is here. Just copy this. This is the first step. Okay, copy this and go to that origin and oops. So go to view and we are going to need the project explorer. Okay, so go to this pants.out.gnu. Now you should add a column here. Okay, you see these are the K points. So let me just write these K points. These are the energy values. What we are actually going to plot is E minus EF. That is, we are going to subtract the Fermi energy from everything so that we get a clearer picture of the band gap. Okay? Okay. So just right click, come to set column values and do call B minus that Fermi energy what we have copied. Okay? Do apply. So now we are going to plot this one. Do line definitely. We don't need this much. Okay? Maybe we will plot only minus 8 to 8. Okay. Do apply. Okay. So it is now plotted. You see, for horizontal, we are going to start from 0. Up to which point we are going to go? That's the question, right? For that, go to these output files once again, and you should go to this bt bats.out. Okay? Well, you see, the last point for your K points section is 3.2802. Just copy this and paste this particular value here. Paste. Apply. Okay. Definitely, for band structure, the title and format are like this. Don't put any tick here. Okay. But we are going to come here later. Okay. This has a purpose for now. Okay. Now go to top, do show axis and tricks, and definitely do none. For this also, do none. For left, leave as it is. For right, and it is already done. Okay, apply it. Okay, now we have done something, but we have to do it better. For that, what you should do is go to this output file again. You see, these are the points calculated, okay? And these are the x coordinates of the symmetry points we have provided in the input file, okay? Okay, so let's go to the input file first. This is the input file, and you see, in our input file, the points were gamma x m, gamma r x, okay? So here also we will have 6 points. So this is gamma x m, gamma r x. Okay. So the next point is 0.5. What we are now going to do is we are going to draw a straight line at exact 0.5. Okay. So take this line tool, go to 0.5, press shift and go up to the margin. Okay. So when you are pressing shift and drawing this, it is going to be exactly straight. Okay. Well, so this is done. Now the next point is at 1. So that is also trivial, no big deal. The next one is 1.7071. This is not going to be easy. So we have copied it and just go here and go to custom peak levels, do special, put the value here at axis value this, and do apply. Now you see, you can see the 1.707 line. Okay. So now we are again going to take a straight line. Okay. It's done. Now the next one is 2.5731. Similarly, we are going to do this. Now we don't need these ticks anymore. Okay. So just go to title and format and do none here. Apply. Okay. So just delete these two. So what we are going to write here instead? Definitely, we are going to take a text box and write G. Just, I know this is gamma, but for now write G. I will tell you what to do. Write X here. So these are your points. Now, take this G and click on this Greek. So this is going to be gamma del. Similarly, do it for this one too. Okay. So now the band structure is complete. Do it better. Now it's time to export this. Okay. For that, go to File, Export Graphs, open dialog. For that, definitely if your guide has preferred something, do that. Otherwise, what I prefer is PDF. So just do PDF here. Definitely resolution should be 600. Go to PDF options, make it 600 here too. And where should it be exported? That is the location, and just click OK. So apply. Let me go to desktop now. You see, the graph has been generated, and that's your band structure. So congratulations, now you have known how to calculate the band structure. Okay, well, so let's meet again in the next video.